It's my pleasure to introduce Valentina, who was recently accepted as a PhD student at Charles University. She will talk about globalizations of L-infinity algebras associated to dg-manifolds. This is her first talk on this subject. Please, Valentina.
Okay. So thank you very much for the invitation. So the purpose of this talk is to explain about two L-infinity structures on the space of vector fields on a Q-manifold. So I have divided this talk in three parts. I'm sorry, I think it's not working. Yes. Okay, thank you. So I have divided this talk in three main parts. So first, we are going to start with the definitions of the objects that we will be working with, which are Q-manifolds, also known as dg-manifolds, and L-infinity algebras. Secondly, I will explain the two mentioned L-infinity structures on the space of vector fields. And lastly, we will try to explain further generalizations of higher algebras associated with graded manifolds. So by a graded manifold, we mean a graded, sorry, by a Q-manifold, we mean a graded manifold that can be Z, Z2, or N-graded, supermanifold together with an nilpotent operator. The typical examples are the shifted tangent bundle and Lie algebras. So in the first case, we identify the space of functions in the shifted tangent bundle with differential forms. In this case, the role of the homological vector field is played by the RAM differential. In the second case, we have a similar situation in which we identify the smooth functions on the shifted vector space, G1, with cochains. So in this case, the role of the Q field is played by the Chevalley-Eilenberg differential. So these are the main examples of Q manifolds. And now we would like to introduce a more algebraic concept, which is an L-infinity algebra. So for this, we need to take a graded vector space L. If we consider graded symmetric brackets Lk from the kth power of L to L, and they satisfy the so-called generalized Jacobi identity, which is this formula, which is written here. Then this L space will be referred as an L-infinity algebra. And I know that this formula doesn't say too much to us, but I am going to explain in the following what is the meaning of the first identities. So in the first case, we will obtain that the square of L1 would be 0. So this means that we can talk about a cochain complex, and we have a differential here. Secondly, we will obtain this formula, which is written here. So this is just telling us that L1 is not only a differential, but a derivation with respect to the product. And the third identity is given by this expression here. So if we are working in the cohomology of L, we will have that these last four terms that we have here, these last four terms are going to be 0. So we will just obtain the usual Jacobi identity. So the meaning of this is that we will have dg-LA structure on the cohomology of L. So what we can say here is that an L-infinity structure is a generalization of a dg-LA. So now we would like to make a relationship between the two previously defined concepts. I mean, I want to establish the relationship between a Q-manifold and an L-infinity algebra. So this is given as follows. If we start with the L-infinity algebra, if I have a graded vector space L endowed with the brackets that I mentioned before, I can obtain a homological vector field and a graded manifold by just thinking about the graded vector space as a graded manifold. So we just define the homological vector field by this expression here. So we just construct a Q field out of the L-infinity brackets. And we can prove that this object will be homological if the brackets are satisfying the conditions in the definition of an L-infinity algebra. So we see that it's like an equivalent concept to think about Q-manifold or an L-infinity algebra. And we can also do it in the opposite way. we can start from a general Q manifold and produce an L-infinity algebra on the tangent space at a given point. So what we do now is to consider a Taylor expansion of the homological vector field Q, which is written here. So I just take an arbitrary point and make the Taylor expansion with respect to the local coordinates. So we will obtain, in general, a constant term, which is given by this expression here, Qk of p is the constant term. If we have located in the zero locus of the Q field, this term vanishes. So in this case, from the coefficients of the Taylor expansion, we can define the L-infinity brackets. So the prescription is as follows. We just set a basis on the tangent space at the fixed point, and we define the L-infinity brackets by this formula. So we just extract the coefficients for the Q field, and we define the action on the vectors in this way. So given in this formula, we can define that this satisfies the condition in the definition of L-infinity algebras. But in general, we can have that this point is not at the zero locus of the Q field. In such case, the constant term will be known as the curvature for the L-infinity algebra. And in that case, we will be talking about curved L-infinity algebras. So we see that this construction is of local nature. So we see that it's highly dependent on the coordinates. So we wish to have a more global construction, which is invariant under the coordinates. Okay, so that's what we wish to do now. We would like to make a globalizations of the L-infinity algebras. That's why this talk is called like that. And one of the ways to fix this problem of the highly dependence on the coordinates is to consider this fiber bundle, which I just consider at a given point x. I consider the fiber given by this expression here. So the elements in this fiber can be thought of as vectors with coefficients being a formal power series. So if we want to be more concrete, I just fix the base point, which is given by x. I denote by y i's to coordinates on the tangent space, and pj's are coordinates on the cotangent space. And then we can produce this expansion. So this is how a typical element in the fiber looks like. The idea now is to prove that this space of sections of this bundle are a Lie superalgebra, and the space of vector fields on the Q manifold will correspond to an abelian subalgebra here. So I will explain why is this useful then. I'm going to talk about the construction of derived brackets later. So to start with, as I mentioned before, we need to prove that the space of sections is a Lie superalgebra. So I need to define the Lie bracket. So first, if I consider two elements in the fiber, AX and BX, then the definition for the Lie bracket is given by this. If you look carefully, this looks similar to the usual Lie derivative, or Lie, the vector, how to say, the Lie bracket of usual vector fields, because we are considering directional derivatives here with respect to the A field and then in the other way around. So given this definition, we can prove that L is a Lie superalgebra. And now, this is the main construction that I'm going to apply. So in order to define L-infinity algebras, this is a construction that is very useful to use. So I will be applying this everywhere. So this is the setting. Suppose I have a Lie superalgebra, which is the case that I have in my construction, and together with an nilpotent operator. If I am able to find a projection from the Lie superalgebra L onto an abelian subalgebra, then I can define an L-infinity structure on the abelian subalgebra. So in our case, the abelian subalgebra is the space of vector fields on the Q manifold. So this is precisely where I'm going to define the L-infinity structure. So this will follow from this proposition. So yes, that's what I'm using. So yes, yes. Okay, Theodor Boden. Yes, I don't know how do you, okay. Yes, that's him. So in my case, I need to define what will be the nilpotent element that will produce the L-infinity algebra. So in order to produce this nilpotent element, delta, I will apply some lemmas that are similar to the ones given in Fedosov deformation quantization. So this is what I'm going to do now. So as I mentioned before, it's important to have in mind that the space of sections of the bundle that I mentioned before is the Lie superalgebra. The abelian subalgebra will be the space of vector fields inside this other bundle. So now we need to find the delta operator in the previous proposition to construct the L-infinity brackets. And to do this, I need to use these lemmas, Fedosov lemma. So this is similar to the lemmas used in deformation quantization. So we start with the torsion-free connection, nabla. We can deform this connection by a differential form R in such a way that this operator is nilpotent. So the idea is that thanks to this operator, I can produce a bijection between the sections of the tangent bundle, I mean the vector fields, and the covariantly constant sections of the fiber bundle that I'm considering. So, okay.
Square is zero or some power?
This square is zero. Yes, yes. I think, I'm not sure, but I think nilpotent is the square. It's referred to the square. And idempotent is any power. Okay.
Maybe I lost track of the motivation. So what you showed that given a Q manifold, at any point you can use the tangent space that build an L-infinity. And so what is the step, the extra step you're taking now? You want to build an L-infinity?
Yeah. I mean, because that construction, first you need to fix the point and take a local chart and construct the L-infinity algebra on the tangent space. But we wish to have...
Use the chart to write the formulas, but once you wrote the formulas, I think the brackets don't depend on the coordinates.
No, because you see that in the previous slide, like here, you are taking Taylor coefficients of the Q field. So like you wish to have a global construction of this. Like you want to define an L-infinity algebra in the space of sections of the tangent bundle. Yes. Yes, on vector fields.
Saying some form of power series coefficients. So what role will they play?
I mean, what I mean is that here, if you change the coordinates at the given point, you will obtain a different definition for the L-infinity brackets. And in general, you can have curvature. Like a curve L-infinity algebra. Yes, I mean, L1 square is not necessarily zero if you are not in the zero locus of the Q field.
Okay. So Q squared is zero everywhere, but L1 is not.
Yes.
Is not zero everywhere.
Yes.
So you want to do a construction that works even away from the zero locus.
Yes. And also, as I don't know if this answers your question, but even if I fix the point in the zero locus, you know that I have this definition here.
Yeah.
It depends on the Taylor coefficient of Q. But if I change the coordinates or if I change the way in which I read the point, this can be different.
Okay. I see what you mean by coordinate dependence. So the homogeneous parts of the field expansion
Yes.
are coordinate dependent. Yes. Okay.
Yes. So that's the problem that we have. Oh,
But-
sorry if I'm going too fast.
Yeah, that's fine.
Maybe.
But then when you slides later, you mentioned use this formal power series. So what do you think?
Yes. Yeah. So now the idea is to. Okay. No, I mean, I would like to apply the construction of derived brackets and think about the space of vector fields as an abelian subalgebra inside this bundle, inside sections of this bundle, and apply the proposition given by Borenov.
But what are these sections? So these are vector fields.
They are usually called formal vector fields. So you have, I mean, if you fix base point x, you will have something like, this is like tangent vector, whose coefficients are a formal power series.
But then another
On
slide,
the
you say
tangent
you
space.
fix sections
Of this bundle.
this bundle. So now
Yes.
they're not formal. They're varying from point to point.
Yes.
Finite formal means that this is the completion, like this is part of series.
No, I understand the connection, but then, okay, in the slide, you have gamma.
Yes.
This S hat tensor
Uh-huh.
T. So that means that you also have dependence on base coordinates.
Yes, if you take a
Just-
It depends on two coordinates. One is space, another is form.
Yeah, but why do you have to? Okay.
yes. Or I don't understand the problem. I mean, what you're asking.
Cool, okay. Maybe
Okay.
Like
you
the
can-
linear part of this would be just n about potential form. You can review this linear amplitudes too.
yeah,
But they also depend on the point of the place.
yeah, I understand.
Mhm.
But here is a generalization of the form. Instead of one linear.
But is the idea to look at those sections of sections of the tangent bundle together with the Taylor series at every point? And then the holomorphic ones that, sorry, the holonomic ones that have the formal series coinciding with the actual tables. Okay, all right, okay.
Okay. No, thank you for your questions. Okay, so as I was mentioning before, I would like to apply the derived brackets construction. So I need to obtain this nilpotent element in the sections of this bundle. Let me see. I think I was just here. Okay. So as I mentioned before, I will obtain this Fedosov connection D. And thanks to this connection, I will have a correspondence between the space of vector fields and covariantly constant sections in this bundle. So now this is my notation. I will take a vector field X on M, and I will denote by X hat to its corresponding section in the bundle. Okay.
So the theory says that there exists a bijection.
Yes.
But the bijection is that for every vector field, you take its Taylor expansion at a point, and then add that to the section. And is that the bijection? It's not. So what is it?
No. I think I mean, you start with Q, and suppose you have to obtain this object here, its corresponding object. So it will be an expansion. It will start with Q plus, and you will have first covariant derivative, then you will have a term which is dependent on the curvature, second covariant derivatives of Q, and so on. Like you will have a power series.
Yes.
I
think that's what I said.
Okay.
If Q is an element of gamma Tn, at every point, you take its Taylor expansion.
Okay. Yes.
Then that would be the S hat star information. and you take those two together,
Yes.
it's going to be a section of this. Is that?
Yes, it was. It works like that.
So I understand because you represent the Taylor series. Yeah. But what my question was, what was that? Okay. So
Yes. So it works like that. Okay. Okay. Continue here. So now we apply this lifting, this correspondence to the homological vector field Q. So we will obtain an object here in these sections of this bundle, which is corresponding to Q. And now we can apply the derived brackets by Voronov. So now we are in the conditions of the proposition. So in this case, I checked in my thesis like the Jacobi identities for the brackets. And I didn't obtain that the square of lambda1 was 0. In this case, I will have a curved L-infinity algebra because we are, you are taking any point, so you can have a curve term. In this case, the unary bracket will be given by this expression here. So if you take any vector field x, you will need to apply the covariant derivative along x of q. And next, by the general definition of the brackets, I will obtain an expression like this. I didn't write explicitly the formula because I think it's not necessary to go into these details. In general, I will obtain this expression, which is just the formula for the derived brackets. So now, this is just the first L-infinity structure that I want to define. But there's a different approach to define an L-infinity algebra on the space of vector fields. So this was done by these authors, Mehta, Stienon, and Xu. They proved this result that you can endow the space of vector fields with a L-infinity algebra. But in this case, they don't have a curvature term. They have one order map given by the Lie derivative along Q, which is
That has to be somehow answered. So on any vector space, you can introduce L-infinity algebra and you say that everything is trivial, everything is trivial. So what makes these statements non-trivial?
Okay. Well, I'm not really sure about that, but I think this structure is it's very important because if you consider the second term, this is related to the so-called Atiyah cycle.
The previous one, this previous one, somehow non-trivial or?
I think I'm in the process of understanding the applications of this algebra, but this was a work done in relation with gauge systems. So I know that it has applications there, but I don't know.
Not actually exactly because the Jacobi is not satisfied and you're expanding to something like this.
Yes, I think so. Okay. Okay, so in the case of this construction, as I said before, we don't have a curvature term. We just have the first bracket, which is given by this Lie bracket along Q. And secondly, we have that the second order map is given by the so-called Atiyah cycle, which is given by this expression here. In general, they have a recursion relation for the higher maps. So they prove that the higher maps are just determined by the second map and the curvature of the connection. So now I would like to summarize the differences between the two structures. So first, in the first case, in the Fedosov Lie construction, we have a curved L-infinity algebra. Secondly, if we start from a torsion-free connection, we can compare the first bracket for the Kapranov L-infinity algebra and with the other procedure. We can compare it in this way. As I showed before, the first order map is given by the Lie bracket along Q. Instead, in the other construction, we just have this covariant derivative. So you see that the differences are just for one term. So in the second case, we just lack the other covariant derivative. So this is like one of the differences that we have between these two structures. And now this is what I did in my master thesis. Like I studied these two L-infinity algebras. What we wish to do now is to understand from a more general approach how to obtain these two L-infinity algebras, or how to connect these two constructions. So this is what we wish to have. So the first steps that I have been working with are to consider the geodesic exponential map. If we consider this map, we know that we have a local diffeomorphism of fiber bundles. So what we do is that we consider the homological vector field Q, which will be a vector field in the base manifold of these fiber bundles. And we try to associate a lifting to this vector field, which will be a vector field in the product manifold or in the tangent bundle. So depending on how we lift this Q field, we will reproduce one or the other L-infinity algebra. Okay, so how to explain this better? As I mentioned, you can consider the full lifting of Q or just the vertical lifting. So in the first case, if I consider the full lifting of Q, I will obtain the Kapranov L-infinity algebra. And by Kapranov, I mean the algebra exposed by the authors, Mehta, Stienon, and Shu. So, okay, if I take coordinates on the tangent bundle and I consider the geodesic coordinates in the flat case, I can write the Q field in this formula, in this way. So now again, we apply the derived brackets given by Voronov, and I will obtain, as I mentioned, the Kapranov L-infinity algebra. On the other hand, if we just compute the lifting by this vertical way, we will reproduce by the derived brackets construction, we will obtain the Fedosov-like procedure, like the curved L-infinity algebra. In the first case, I obtain the one which has no curvature. In this case, I obtain the one with curvature. So what I'm trying to do now is to consider the general case in which I have curvature, because you see that in this case, I have been working with these flat coordinates. So I'm just taking the linear geodesic and computing at time equal 1, sorry. So this is the correspondence between the coordinates. But in general, this is not the case. So we have to take in mind the curvature of the connection. But this is something that I need to compute. I still need to compute this case. So first, what I'm going to do is to express the geodesic coordinates in terms of coordinates on Tm by expressing y in a formal power series in the vector eta. What we wish to do now is to reconstruct the Fedosov connection in this approach. And what we expect to have is to reconstruct the Kapranov and the curved L-infinity algebra from these general coordinates. But this is something that I still need to do, like it's something in progress now. I think that's all. I'm not sure if I should mention something else. Thank you. Okay.
Well, so we did some questions. Some more questions from the audience.
Okay.
What is the algebra again?
But do you mean in this general case or in the in the Fedosov? Okay. Okay, in that case, the abelian, let me go back. Okay, so we were working with this bundle.
Yes.
So we identify the abelian subalgebra with the sections of Tm, with the vector fields on M.
First, these sections themselves are super algebra.
Yes.
Just using the usual bracket.
Yes.
Extended.
Like you do it pointwise.
Yes.
So okay. So you extend this Lie superalgebra in each fiber to the sections of this bundle. So you see that the sections of Tm are a subbundle of this. And this will correspond to the abelian subalgebra of these sections.
Why is it the
I can try to write.
Yeah.
Okay, because it's not. Okay. Maybe here it's okay. So we know that if we fix the point, we have an element here, like this way. This is a formal power series on y coordinates. These are coordinates on Tm. And we have something like this. But here I'm identifying this with, these are coordinates on the cotangent space. So it's like I can make an identification with this to del xi at the point x. So now when you take a section here, let's start. I need to vary the point, right? So like this frame is just moving in the local chart. So I will write something like this. Now this coefficient is moving with x as well. So you have like usual smooth function at the base and formal power series in this variable. And now you can write something like this. Okay. So the thing is that, let me go to the definition of the Lie bracket. I have this definition here. So you are always taking derivative with respect to y coordinates. Like you fix the point and you make this derivation along y.
Pointwise bracket is formal field.
Yes, yes. That's why if you have a usual vector field, like just depending on x, not on y, you will have 0 in the bracket because this is independent on y on the formal
It's a
coordinate.
bit confusing because you wrote d by dxi, and it's better to write d by y.
Okay. Okay, it's okay. So something like this. Mm-hmm.
So that describes the bracket in the Fedosov like section.
Mm-hmm.
But why is the embedding of TM sections obedient with?
Because you are considering derivations with respect to the formal variables here, and you are thinking of the vector fields on M with respect to this bracket. So you are not, you will get 0 because you are independent on this y coordinate.
How are you embedding TM sections? It's not.
I'm just considering, let's say, x. I'm just taking the coefficient is dependent on x on the base coordinate.
Yeah.
And I have like the term pi here.
So it doesn't have any y.
No.
But that's different from the organically constant section.
You have this.
Yeah.
This is a vector field. Then you will have a corresponding lifting x hat, which will be covariantly constant section,
Okay.
but it's not the same as the initial object.
Okay. Do you say that somewhere?
I don't remember if I mentioned. Okay.
Okay, so the Abelians of algebra is not using this bijection between the
No.
between.
I mean,
constants and
at least in my case, the space of covariantly constant section is not the same as the abelians of algebra.
okay.
Okay.
Okay, thank you.
And thank you for your questions.
Thank you.
More questions? Okay, let's thank the speaker again.
Thank you.